Hi everyone, today we'll start learning linear discriminant analysis. So we continue our supervised machine learning. Linear discriminant analysis, the LDA. So we use LDA when you want to classify data into two or more groups. For example, if you have this data for the height, we need to check if this height is fit or not fit. So in the logistic regression that we described in the last video, the logistic regression, we describe only the data if it's only two classified, 0, 1. In linear discriminant analysis, it can describe two or more classes. For example, it also can describe fit or not fit data sample. So linear discriminant analysis is the same as logistic regression, but if you have more than two classes, we can use linear discriminant analysis. And also you can keep in your data, when you prepare your data, you can keep like as a numerical data, not just 0 and 1. You can keep 0 and 1, or you can classify it as, for example, fit nor fit. You can have this text value. So why it works best when you predict like height can be separated classes. It's especially useful when you have more than two classes. Logistic regression work well for two classes. LDA extend beyond that. So it is based on bias theorem, which calculate probabilities for each class and then assign the observation to the class with the highest probability. So if you have more than two classes, so the LDA can be a better choice for you. Logistic regression only work with two classify, 0 and 1. And LDA can work with 0 and 1 and more. If you have like fit, not fit, medium fit, more than two classes, you can use the LDA. And it's the principle of work. This is work on based on the bias theorem. So for example, we have this the fit not fit data, and if we want to check the person if it's high and medium height, so probability they are fit is 15 divided by 40, the total for medium. So fit for medium is 15 divided by 40, we get 0.3. And the probability for getting not fit, it is 25 divided by 40. So we have 0.65. So if someone is medium height, the model would predict not fit because that probability is higher. So we calculate the probability of, for example, in this one, fit not fit, and then which the high probability, the model will predict not fit. So model will give you either fit or not fit. But who's the high probability? It is over than 0.5. That means it is not fit. And if it's below the 0.5, that means it is fit. So LDA use bias theorem. And bias theorem, this is the equation for bias theorem. B class bx by class multiplied by b class k and b of x. And to make it easy for you, so this is the equation, bias theorem, and the classification. So the first one, this is where it's called the posterior probability. This is the posterior probability. We're trying to find the posterior probability, where it's tell you if this class it is fit or not fit in our example. So b multiplied by x slash class k, this is called the likelihood. How likely feature x is under that class. So he take all the independent variables, the x variables, and you check how that under that class. And we have b class k, this is a prior probability of the class before seeing data. This is the probability before seeing data. This is called a prior. P class K, this is a prior, and this is the likelihood. Divided by the P of X, which is the total probability of X across all classes. This is have to be normalized. So the class will give you the class with the largest posterior probability wins. Who have the largest posterior probability, he will win. So this is the equation that use Bayes theorem in the LDA to find which has the highest probability. In such case, if you have the easy equation, so this is the same this equation when you find the probability fit for model dividing by medium, just divided by the total of the medium. But it's just in simple case. But in real life, when we have more complicated and when complicated linear, one complicated continuous data like gamma ray or any continuous data, so instead of using this simple equation, so this is the likelihood probability, we will use the conditional probability equation. So B of kx, this is for the likelihood, so we compensate the likelihood with this one, and this equation we will find these parameters. You find the mean of the data. So we assume that each class, fit nor fit, follows a normal distribution around a mean. So in this conditional formatting is the same as the likelihood. This is the same as likelihood, but in this one we assume all the fit and non-fit data, it is normal distributed. First, the complicated formula just same Bayes theorem applied when features are continuous numbers not categorized. So this equation, it is same as the likelihood. It's a BK, it is same as likelihood in here, but this is the easy equation when you have like very simple data, same as we have fit nor fit. But in real life we have very complicated data, very continuous data, gamma ray that it change and with the depth. So any continuous data change with the depth, we need more complicated equation. So this conditional probability will use in the probability to find the best areas. So this one in real life, like continuous features in LDA, things are different. So discrete data like bass, fill, red, blue, etc. you cannot frequent directly. Continuous data like height, gamma ray, log, density, etc. you cannot just count exact matches between every measurement. It is unique. Not two samples have exactly the same dt. And instead we model the likelihood with a probability distribution and usually a Gaussian normal distribution. So this is called the Gaussian normal distribution, and this is Gaussian normal distribution we use instead of the likelihood for more complicated data, for continuous data that changing with the depth, and that we use the LDA. Assume P of X, this is the probability, is equal to n, this is the mean, multiplied by the k, standard deviation, and k. You don't need to worry about all that, we just put symbol code and we get all of them together. And now we will go to the, I'm gonna go, first I have my first same as data that we use in the classification and the logistic regression. I'm just getting my data. I'm naming my CSV file as df. So my data is contains same price, and in here I need to check it is sold, not sold. This is my 0, 1. As we said, LDA can work with 0 and 1. And also you can name this one is not fit. You can name the one is fit. Fit not fit or 0, 1 is the same. You can apply it in the LDA. So first, if you want to fit the LDA fit, So firstly, you have to library this packages. It's called mass. You need to find the mass and upload and install the packages mass. Just click on it. If you don't know how to do that, just go for install and buy the mass if you don't find, and click on it and download it. So install.fit equal to LDA. That's gonna fit the model. So LDA equal to, I need my y is sold, and I need my tilde dot and my data equal to df. I'm gonna run this one. So this is LDA, my dependent variable is sold. I need to check if it's this houses, how much houses sold or not, same what we did in the logistic regression, but we use the LDA and we compare between them which the best, and when you run the LDA instead of logistic regression. So Django's LDA.fit is gonna see. So when you first fit your model, this is my y, and this is tilde. This is my tilde, and then this is all. That means give me all the x in my data, and my data is called to df. This is my df CSV file. I'm called a df, and we will get from when we fit our model and you just run it, we will get the first one, prior property of groups. So this is the prior property of the groups that we talk about. This is the prior. We get the prior probability of the class before seeing data. So this is the first thing that we get when we run our fitting model. So we have only two groups, 0 and group 1. From group 1 we get 0.45, 45%, and for the group is 0, that means this is not fit, and this is fit, it is 0.50. This is fit, 0.55, this is not fit. So it's gonna, now we just fit our model. It's gonna predict. So LDA dot is gonna predict our model equal to predict. My model is called LDA.fit, and my data is called df. So let's gonna predict the model on my data, and then LDA dot predict, it's gonna see the $sign. So we have the class, and we have posterior, and we have the x. Let's gonna check the posterior. So in this, the after we fit our model, the predict, we predict our model. After we fit our model, now it's time to predict on our data, and there we get the posterior that we get this the probability of x. So we get the posterior from this equation, so you don't need to worry about the complex formula that we talk about. Let's give you the posterior from here, and the posterior, he will tell you if this sorry for that, and he will tell you if so if you're back, you will see we have two groups. So from the posterior we have 1 and we have 0. So this is 79 chance this house it is sold, and this one it is tell you it is 20% this house is not sold. So one is sold, and this is one is not sold. Okay, and if we need to check the classes, so LDA dot is going to check the class equal to LDA dot predict, and equal to, I need the class, run it, and now give me the table. Let me check the table, same as what we did in the logistic regression. I need the LDA dot predict. Give me the class, and my data is df, I need the solve. Give me the solve from here. Let me check the predicted data with my actual data. So my predicted data, so this is the model we predict. So he predicts 0, where my actual data is 0, 1, 9, 192, and he predicts 0, while my actual data is 1, it is 75. So in here you can compare with the logistic regression. You can compare with logistic regression, which will give you the best, give you the minimum error, and you can choose between them. If you need to find specific, like for example, if you need to run sum, I'm gonna give here sum, give me the sum. I need my LDA predict. I need my LDA predict posteriors, and my aim predict need posteriors minus 1, remove the false if it's equal than, bigger than, example 0.6. Close this one, and here we go. LDA posteriors is bigger than, sorry for that, it is bigger than 0.1. So we have 140.76. So if you need to find what is the posteriors that have more than 0.6 value, for example, or if you need to find the posteriors that have more than 0.8 value, and we keep this as -1, so we just this is the posteriors we have to group. If we -1, that means we just we just remove the posteriors that equal to 0. We keep only the posteriors that have the positive number, that is have 1. So this way we don't include the 0, we just keep the one that the posteriors that have values that is give us 1 value. That means it is this house is sold and bigger than 0.8. So we have 33 sample, it is bigger than 0.8. They have probability of being 0.8. So this is all you need to know in the LDA. So thank you for your watching, and please leave subscribe and leave me a comment if you have any questions, and see you in the next video.